Space, a vast mysterious expanse dotted with stars, galaxies and planets. It's a canvas painted with the light of countless celestial bodies, each one a beacon of the unknown. The Milky Way, our home galaxy, is just one of billions, each with its own unique story and secrets waiting to be uncovered. It's a realm where the familiar laws of Earth seem to bend and twist. Light itself can be distorted, creating illusions that challenge our understanding of reality. The bending of light, known as gravitational lensing, reveals the hidden mass of the universe, showing us that what we see is only a fraction of what exists. One of the most intriguing aspects of space is its relationship with time. Time in space is not a constant, it ebbs and flows like the tides of an unseen ocean. The movement of stars across the sky is a cosmic clock, ticking away the moments in a dance that has been ongoing for billions of years. Time, as we know it, is but a river, flowing at different speeds depending on where you are in the cosmos. In some places it rushes forward, while in others it meanders slowly. This concept, known as time dilation, is a fundamental aspect of Einstein's theory of relativity. It's a concept that has fascinated scientists and dreamers for centuries. From the ancient astronomers who charted the stars to modern physicists who probe the depths of space-time, the quest to understand time has driven human curiosity and innovation. Imagine yourself drifting through the vast emptiness of space, gazing at the distant stars. Each star is a point of light, a marker in the vast expanse, and as you float, you feel the weightlessness of space, the silence that is both profound and humbling. Up here, far from Earth, time behaves differently. The familiar rhythms of day and night are replaced by the endless cycle of orbits and rotations. The Earth, a blue marble in the distance, spins on its axis while you, an observer in the void, experience time in a way that is both alien and enlightening. It's not the rigid, unwavering metronome we are used to. Instead, time becomes fluid, flexible, almost like a dance. The stars move in graceful arcs, their light shifting and changing as they journey through the cosmos. Instead, time becomes fluid, flexible, almost like a dance. This cosmic ballet is a reminder that time is not a fixed entity, but a dynamic force, influenced by the gravity and motion of celestial bodies. This dance of time is governed by the laws of physics, specifically Einstein's theory of relativity. According to this theory, time and space are intertwined, forming a fabric that can be stretched and warped by the presence of mass and energy. Let's embark on a journey, a cosmic adventure to explore the mind-bending world of time and space. We will travel through the vast reaches of the universe, from the surface of distant planets to the edges of black holes, where time itself seems to stand still. We will delve into the heart of Einstein's theories, exploring the equations that describe the curvature of space-time and the effects of gravity on the passage of time. Understand how gravity warps time, creating phenomena such as time dilation near massive objects like stars and black holes, and explore the tantalizing possibility of time travel. Wormholes, theoretical passages through space-time, could offer shortcuts between distant points in the universe, potentially allowing us to journey through time as well as space. Fasten your seatbelts, fellow explorers, as we unravel the mysteries of the universe's clock. Our adventure will take us to the frontiers of human knowledge, where science fiction meets science fact, and the boundaries of reality are pushed to their limits. Our journey begins with a simple question: what exactly is time? Is it a river, a dance, or something even more profound? Join us as we seek the answers in the stars. We often perceive time as a constant, an unwavering march forward. The ticking of a clock, the turning of the hands on a wristwatch, these are all familiar sights that reinforce our belief in the steady passage of time. 1 second on Earth feels like 1 second anywhere else, right? Whether you're in a bustling city or a quiet village, time seems to move at the same pace. Well, not quite. Einstein's theory of relativity tells us that time is not absolute. This groundbreaking idea revolutionized our understanding of the universe. It's relative, meaning it can change depending on certain factors. This means that time can stretch or compress based on your speed and the gravitational forces acting upon you. Imagine time as a flowing river. Just as a river can speed up or slow down depending on the terrain, so too can time. On Earth, the river flows at a certain speed. This is the familiar passage of time we experience in our daily lives, but as you move faster or enter a strong gravitational field, like the one around a black hole, the river of time speeds up or slows down. This phenomenon is known as time dilation. This change in time's flow is called time dilation. It's a fascinating concept that has profound implications for our understanding of the universe. Two key players influence time dilation: gravity and speed. The stronger the gravitational pull, the more pronounced the effect. The stronger the gravitational pull, the slower time flows. This means that time moves more slowly near massive objects like planets and stars. Similarly, the faster you move through space, the slower time passes for you relative to someone standing still. This effect becomes more noticeable as you approach the speed of light. These concepts may seem strange, even unbelievable at first. It's hard to wrap our minds around the idea that time is not a fixed entity. However, they have been proven by countless experiments and are essential to understanding the workings of our universe. Scientists have observed time dilation in action, from the behavior of particles in accelerators to the precise timing of GPS satellites. In the next section, we will explore a famous thought experiment that illustrates the bizarre effects of time dilation. This thought experiment, known as the twin paradox, will help us delve deeper into the strange and fascinating world of relativity. One of the best ways to understand time dilation is through the famous twin paradox. Imagine two identical twins, let's call them Alice and Bob. Alice stays on Earth, while Bob embarks on a high-speed journey into space. Bob's spaceship travels at a significant fraction of the speed of light. As he zooms through space, time slows down for him relative to Alice back on Earth. Let's say Bob travels for 10 years, according to his clock, and then returns to Earth. Upon his return, Bob is astonished to find that Alice has aged significantly more than he has. She might be 60 years old, while he is still a relatively young man of 30. This discrepancy in aging is a direct result of time dilation. The twin paradox, while a thought experiment, highlights the very real effects of time dilation. It demonstrates that time is not a universal constant, but rather a fluid entity influenced by speed and gravity. We've explored how speed affects time, but what about gravity? Gravity, the force that keeps us grounded on Earth, also has a profound effect on the fabric of time itself. This concept, though mind-bending, is a cornerstone of modern physics and has been confirmed through various experiments and observations. Einstein's theory of relativity also predicts that gravity warps time. This means that time doesn't flow at a constant rate everywhere in the universe. Instead, it can speed up or slow down depending on the strength of the gravitational field. Imagine standing on a high mountain. Time would pass slightly faster for you than for someone at sea level, because the gravitational pull is weaker at higher altitudes. The stronger the gravitational pull, the slower time flows. This phenomenon is known as gravitational time dilation. It's not just a theoretical concept, it's something that has practical implications, especially in the realm of space exploration and satellite technology. For instance, the Global Positioning System, GPS satellites orbiting Earth, have to account for this time dilation to provide accurate location data. Think of a black hole, a region of space-time where gravity is so strong that nothing, not even light, can escape. Black holes are the ultimate time-warping machines. The gravitational pull near a black hole is so intense that it can stretch and distort time to an extreme degree. This makes black holes fascinating objects of study for scientists trying to understand the nature of time and space. If you were to observe a clock falling into a black hole, you would see something extraordinary. As the clock approaches the black hole, its ticks would become slower and slower from your perspective. This is because the gravitational field is getting stronger as the clock gets closer to the black hole. As the clock gets closer to the black hole, it would appear to tick slower and slower, almost as if time itself is being stretched. This effect becomes more pronounced the closer the clock gets to the event horizon, the boundary beyond which nothing can return. Eventually, at the event horizon, the clock would appear to stop altogether. This is the point of no return, where the gravitational pull is so strong that not even light can escape. From an outside observer's point of view, time seems to freeze at this boundary. This is because the immense gravity of the black hole is stretching time to its limit. The closer you get to the black hole, the more extreme the time dilation becomes. This stretching of time is a direct consequence of the warping of space-time caused by the black hole's massive gravitational field. The movie Interstellar provides a visually stunning depiction of this phenomenon. In the film, the characters experience time dilation firsthand when they venture close to a massive black hole. The movie does an excellent job of illustrating how time can flow at different rates in different gravitational fields. Astronauts landing on a planet near a black hole experience time at a much slower rate than their colleagues on a spaceship orbiting further away. This difference in the flow of time is not just a plot device, it's based on real scientific principles. The closer you are to a massive object, the slower time moves for you compared to someone who is farther away. This difference in the flow of time leads to dramatic consequences in the film. When the astronauts reunite with their colleagues, they find that while only a few hours have passed for them, decades have gone by for those who stayed behind. This stark contrast serves as a powerful reminder of the strange and fascinating ways in which gravity can influence time.